In this video, we'll talk about how we can prove a function is injective using our definition. So let's recall the definition. A function f from s to t, we say that it is injective or one-to-one if whenever I have two inputs a and b that are not equal to each other, then f of a is not equal to f of b. So that's saying their outputs have to be different. Anytime I have two different inputs, their outputs have to not be equal. Well, I can state that equivalently using the contrapositive, which would say, well, if the conclusion is false, meaning if f of a actually equals f of b, so if two outputs are equal, then the if part has to be false. So then a has to be equal to b. So this would be saying if the two outputs are equal, well, then the only way for that to happen is if the inputs are equal. That's what it would have to take for it to be injective. So we typically use this structure when we do proofs of injectivity. So, well, how do we prove something is injective? What are the steps? So I'm going to use the structure here where first I'm going to let a and b be arbitrary elements of S. So they're arbitrary elements of the domain. And the if part I get to assume is true. So I get to assume f of a is equal to f of b, that their outputs are the same. And what I want to show is the then part. I want to show that will mean that a has to be equal to b. The only way for that to happen is if these inputs were actually the same thing. Okay, so on the flip side, if I want to show something is not injective, I would have to find two different elements, a and b, that are in S, such that f of a and f of b are equal to each other. If two different inputs have the same output, that's bad. Then it's not injective. So let's do an example. I'm going to let L be this function where the domain is reals that are greater than or equal to 0. The codomain is the reals. And the formula for the function is L of x equals x squared. Part A says, show this thing as injective graphically. So if I draw some axes and think about the graph. So draw some axes. Let's think about the graph. So I know the graph of y equals x squared is just a parabola with the vertex as the origin. But the domain here is not all reals. It's just the reals that are greater than or equal to 0, which means I have to only look at the part of the graph where the x values start at 0 and then are bigger than 0, which is just the right-hand side of the parabola. So let's erase this and let's draw just that part of it. So it's just this part of the parabola. Okay, and if I look at that, we saw in the last video that a function is injective if it passes the horizontal line test, which this does. This passes, I'm just going to abbreviate it, HLT for horizontal line test, which means, yeah, it is injective. At least graphically, it is injective. Now in part B, let's actually prove this thing is injective using the definition of injectivity. So we're going to use this structure to prove this thing. So let's start off our proof with scratch work as we typically do. So what it is that I'm given, slash I know, slash I get to assume is true. Well, we get to assume that, let's see, that a and b are in the domain. So we get to assume that a and b are in the domain, which is the reals that are greater than or equal to 0. And we also get to assume f of a is equal to f of b. F of a is equal to f of b. We assume that those things are true. And what I want to show at the end of this is that a has to be equal to b. A has to be equal to b. And one thing I'm getting a little sloppy about is my function is called L here, not f. So let's fix this because I wrote f of a and I wrote f of b, but let's write L. So L of a is equal to L of b. Well, okay, what does it mean that L of a equals L of b? So if I plug into my formula, that means a squared, that's the left side, equals b squared. So somehow from this, I need to be able to conclude that a equals b. So it might be really tempting to square root both sides of this, and I might remember, oh yeah, if I square root both sides, I get a plus or minus. But unfortunately, that's not one of our properties of real numbers that we get to assume and work with in proofs. In fact, that's actually the heart of what we're trying to prove here. So I don't get to just use that of square rooting both sides of an equation here, unfortunately. Okay, but nonetheless, I think I have somewhat of an idea, and for the sake of conciseness, let's dive into the proof here rather than completing the entire scratch work, which I ordinarily would do. Okay, so for my proof, we start off by writing down what it is that we get to assume is true. So I'm going to let A and B be elements of the domain, the real numbers that are greater than or equal to 0. With the property, I also get to assume that L of A is equal to L of B. Okay, then I can write down what that means. L of A being equal to L of B. This means that A squared equals B squared. And while I cannot take the square root of both sides, because that's a property that I don't get to assume is true, what I can do is I can move terms around. So I can move everything to one side to get A squared minus B squared equals 0. And now I can use my difference of squares property. I can use my difference of squares property to get that A minus B times A plus B equals 0. Well, okay, this implies that either the first thing in parentheses is 0 or the second thing in parentheses is 0. Okay, so we got these two cases to consider. So two cases. The first case is A minus B equals 0. If I rearrange this, this would be saying that A equals B. If I rearrange the other one, it would be saying that A equals negative B. So in case 1, that's if A equals B. Well, then that's exactly what I want to show. So then we are done. So in this first case, that's awesome. But we have this other case to consider. Case 2. Well, what if A is instead equal to negative B? Well, so one of the things that I know about A and B is that they're both greater than or equal to 0. So since B is greater than or equal to 0, this means that negative B would be less than or equal to 0. So A is equal to negative B. So this would imply that A is less than or equal to 0. But I know from earlier, we know that A is also greater than or equal to 0. That's what we assumed is true. But we know A is greater than or equal to 0. So for A to be greater than or equal to 0 and less than or equal to 0, this implies the only way that can happen is if A equals 0. Okay, so if A equals 0, I can plug that into this equation to get the value of B. So then, plugging in to A equals negative B, we get, if we solve for B, we will get that B is also equal to 0. Okay, so in case 2, A ended up being 0, B ended up being 0, so they're the same. Thus, even in this case, the A and the B are equal to each other. So in both of the cases, we reached the same conclusion, that A equals B, which is what we wanted to show. Okay, so thus, A does indeed equal B, and that proves, so this function L is injective. And that concludes our proof. So notice again the structure of it. To prove something is injective, we take two arbitrary elements of the domain, in this case, two arbitrary elements that are greater than or equal to 0, and then we assume that, well, their outputs are equal, that L of A equals L of B. And then we do manipulations to eventually get, we want to eventually show that those inputs had to be equal. And if we show that, that means the function is injective.